So we've been talking about analyzing internal combustion engines. We know that we're going to use air standard analyses for these engines where we neglect combustion, assume that all processes occur in a closed system, we assume that all processes are reversible, that the working fluid is ideal gas, and sometimes we'll also assume that that ideal gas has a constant specific heat. Now, we know that this isn't strictly true, but it helps us to model different types of internal combustion engines. Last class, we talked about the Otto cycle. Now, the difference between the Otto cycle, the diesel cycle, and the dual cycle come in how we add heat to the system. In the Otto cycle, we add heat at constant volume. So we can see that when we draw this PV diagram, that this happens on a vertical line in a PV diagram. If we remember back to the first third of the class, when we were talking about PV diagrams, we said that the work under a particular process could be determined by taking the integral of PDV, or the area under the line for the process. So here you see when we're adding heat and rejecting heat at constant volume, there's no work involved in those processes. So it's this constant volume heat addition that makes an Otto cycle an Otto cycle. Today, we're going to move on from the Otto cycle and talk about diesel cycles. In these diesel cycles, we typically have compression ignition instead of spark ignition like we see in the Otto cycle. So the difference between the Otto cycle and the diesel cycle is that in the diesel cycle, the assumption we make when we're adding heat is that it happens at constant pressure. So just like in the Otto cycle, we'll have 4 internally reversible processes. First, we'll have isentropic compression from state 1 to state 2. Here's the difference. When we add heat, we're going to assume this happens at constant pressure. Notice that now on this heat addition process, we have a horizontal line on our PV diagram. Then we'll also do an isentropic expansion. This is the power stroke, similar to what we have in the Otto cycle. And then constant volume heat rejection. So even though we're going to assume that heat addition happens at constant pressure in the diesel cycle, we'll still assume that heat rejection happens at constant volume. So what's the difference, right? As I look through each one of these processes, remember before for the Otto cycle, each one of these processes was a simple process, meaning that there was only heat or work. We'll see that's not strictly true for the diesel cycle. We'll still have power going in our compression stroke from 1 to 2. But when we add heat, we'll notice we're not just adding heat here. Instead, because this happens at constant pressure, we have a horizontal line. So if I take the integral of PDV as I move from state 2 to state 3, I'll notice that as I'm adding heat, I'm getting some work out. Then I'll transition to state 3 to 4. This process is the power stroke, although now for a diesel cycle, we'll talk about having a 2-stage power stroke because we get some power out while we're adding heat and some out here in this purely power stroke. Finally, we'll have heat rejection as we move from state 4 back to our initial state, state 1. So the difference here between the Otto cycle and the diesel cycle is what happens when we're adding heat. In this case, we're adding heat at constant pressure. Now, the interesting thing here too, right? Remember when we did the Otto cycle, there were only 2 volumes in the problem. There was the small volume and the big volume. But now there's 3 volumes. So even though state 1 and state 4 have the same volume here on my PV diagram, state 2 and state 3 have different volumes. So we can't talk about only one volume ratio in this cycle. So here we do have this 2-stage power stroke. And this is one of the things that trips us up when we start to work on the diesel cycle here, is that we have to worry about heat and work when we're adding heat. So let's do a first law analysis on the different processes in this cycle. So as I move from 4 to 1, this is the heat out or the heat rejection part of the process. we know that we can take the first law, we can use it either extensive or intensively, divide everything by mass, which is constant. We know that for this process, there is no work or power. This is a simple process with only heat rejection. So I know that as I reject heat when I move from state 4 to state 1, that's going to be m times u1 minus u4. Or if I want the specific heat, then that would be little q is equal to u1 minus u4. When I deal with adding heat, things get a little trickier because now this isn't a simple process. Just like I showed before, we have heat transfer and work for this process. So remember, we learned how to do this in the first third of the class. We know that this work is going to be the integral of P dV. Now the calculus here isn't too bad because my pressure is constant. So what I do here is I can move this pressure outside of my integral term, and I get that the work here is the pressure times V3 minus V2. Now, I called this P2, but I could have said P3 here too, because P2 and P3 are the same, because this is constant pressure heat addition. So now I can rearrange to try to find an expression for the heat in. Now I notice that I have U3 minus U2 plus P2 times V3 minus V2. So I can sort of arrange my terms like this, separating U's and PV terms, but I could also group these things together by their state number. So here, what I've done is I know that this pressure, P2, is the same as P3. So over here, I have U plus PV, and that's all at state 3. And then I have minus U2 plus P2V2. Now, you could have alarm bells ringing in your head because maybe you're sitting there thinking, oh, Professor Schertzer, I know what U plus PV is. It's H, right? So in this case, we can, even though we got this from the closed version of the first law, to make our lives a little bit easier so we don't have to look up things like U and P and V, we can just say that the heat transfer in from state 2 to state 3 is H3 minus H2. Now here's a little trick that I like to use to remember this. So if this was an Otto cycle, we would find that Q from 2 to 3 was U3 minus U2. Now the difference between the Otto cycle and the diesel cycle is that in the Otto cycle, we have a vertical line where we're adding heat. Here in the diesel cycle, we have a horizontal line where we're adding heat because we're doing this at constant pressure. And when we have that horizontal line, the U terms turn into H terms. So we have H terms at the state points that touch this horizontal line. And lo and behold, H is the first letter in horizontal. So if you have a line that's horizontal on your PV diagram for your diesel cycle, you can put in H's instead of U's. But as always, you don't have to remember these things. You don't have to think about these silly mnemonic devices. You can just work this out from the first law. Here we use H for convenience. We aren't modeling this as an open system, right? So remember before when we had specific enthalpies, they came about because that was a component of the first law for open systems. So here we're using H, but it's really just a mathematical convenience. So how do I find the net work? So I know this work that comes out between state 2 and state 3 is the integral of P dV, but the pressure is constant, so it's going to be P 2 or 3 multiplied by V3 minus V2. Work from 3 to 4 is going to be just what I would normally find from the first law. I'm going to assume that there's no heat here, that it's a simple process. And then work from 3 to 4 is U3 minus U4. So I'll put that into my net work equation. I'll do the same thing in my compression stroke, and I'll find that U2 minus U1 is equal to Q from 1 to 2 minus W from 1 to 2. So if I isolate for W from 1 to 2, then I'll get that W12 is equal to U1 minus U2. Now I expect this to be negative, so I've left it in red here. Now again, I can use this equation for net work, or this is net work per unit mass, right? Or I can collect terms by their state number. And if I collect terms by their state number, I'll see again that those state points that touch the horizontal line have a u plus a PV term. So I can turn those points that are on the horizontal line into h's. Again, because h starts the word horizontal. I can remember that h3 minus h2 is q in, and u1 minus u4 is q out. So as always, W net is equal to q in plus q out, recognizing that q out is negative. So the textbook will tell you that q in minus q out is net work, but they're putting absolute value signs around those heat transfer terms, even though they don't tell you that. So for this air standard diesel cycle, we end up with essentially the same equations as we saw in the Otto cycle, but what happens is those u terms that touch what's the line that's now horizontal become h terms. Again, you don't need to memorize any of these things, you just work them out from the first law. And now we have symbolic solutions for diesel cycles. If we want the thermal efficiency, we can find the net work per cycle and divide it by the heat in per cycle, which is the same as the heat in plus the heat out divided by the heat in for one cycle. If we work that out here, then we can find that our net work is H3 minus H2 plus U1 minus U4, and our heat in is H3 minus H2. We can notice that H3 minus H2 shows up in the numerator and the denominator, so this becomes 1 minus U4 minus U1 divided by H3 minus H2. Or I can write this down as Q in plus Q out over Q in, which is equal to 1 plus Q out over Q in, recognizing that Q out is negative, and unsurprisingly, I get the same equation. It shouldn't matter which way you derive your thermal efficiency, you should get to the same answer. So, in the Otto cycle, we only had one compression ratio, right? And that was defined by the volume before compression, that's the biggest volume, divided by the volume after compression, which is the smallest volume. So that's still the case for diesel cycles. We still have a compression ratio that's based on the volume ratio as we go from state 1 to state 2. We know that efficiency increases with the compression ratio. The textbook will give you this equation, which is an equation I've never used before, but I can see that if this is 1 minus some term, right? So if my compression ratio goes up, this negative term gets smaller. If my compression ratio was infinity, this term would be 0 and I'd have 100% efficiency, right? Now, obviously that's not realistic, but it shows me that as I increase this compression ratio, my efficiency also increases. But there's also this other ratio that we're interested in, because now we have 3 different volumes in the problem and not just 2 different volumes in the problem. So in the diesel cycle, we have this other ratio that we call the cutoff ratio. Like the compression ratio, the cutoff ratio has to be bigger than 1. So we take the bigger volume divided by the smaller volume. But now the cutoff ratio isn't talking about the compression process, it's talking about the heat addition process. So we take the larger volume in the heat addition process, V3, and divide by the smaller volume in the heat addition process, that's V2. So we have these 2 ratios. The first is the compression ratio, which sort of gives us an idea of the change in volume as we compress the fluid. The next is the cutoff ratio, which tells us about the change in volume as we burn our fuel, right? Or as we add heat to the system. So efficiency in these engines decreases with cutoff ratio. So where we want to have a large compression ratio, we want to have a small cutoff ratio. We can see that here too. So if this cutoff ratio is small, the smallest it could be is 1. If V2 is equal to V3, then this term up here would be equal to 0. And this term would be 0 too. So we can see that from this term. We can see how the thermal efficiency will respond as we change the cutoff ratio. So let's do an example here. We're going to talk about this diesel engine. I'm only going to do this problem as a constant specific heat problem. But if you'd like, you can go through and do a variable specific heat version of this same problem. Or if you want to look at how we do variable specific heat problems, you can go back to our Otto cycle example where we did constant and variable specific heat. So here we're told about some diesel cycle. We're given the mass inside the system. We're told the pressure and the temperature at state 1. We're also told our compression ratio is 17. We're told the maximum temperature in the system is 4,000 degrees Rankine. So here, that happens at state 3. So we increase the temperature as we compress, but then we also increase the temperature as we add heat. If you drew a TS diagram, you would also see that state 3 is the state that has the highest temperature. We're asked to find the amount of heat that's added to the system, the thermal efficiency of the system, and the cutoff ratio. So in order to do that, first, like all thermodynamic cycle problems, first we want to talk about how do we get symbolic solutions, and then we'll need to fix some states in order to find numerical values for these systems. The symbolic solution for heat in. We've talked about this a little bit already, but we can go through it again. So the heat addition happens from state 2 to state 3. How do I find the heat addition? The answer in thermo is often use the first law, and that's the case here. So I can write the first law as an extensive version, or I can divide all these terms by the mass and have an intensive version of my closed first law. Now, unfortunately, or maybe fortunately, because this is a horizontal line here, I'm adding heat at constant pressure. That means there's going to be work involved in this process. How do I find the work? I take the integral of P dV. But this pressure is constant, so I can pull it out of my integral. That's how I move from here to here. And then the integral of dV from state 2 to state 3 is just going to be V3 minus V2. So now I have this equation. If I isolate for Q from state 2 to state 3, then I can group my terms by their state number, right? Recognizing that P2 is equal to P3. So here I can say P3 times V3. But over here, I can say P2 times V2. And I notice that I get U3 plus P3V3 minus, in brackets, U2 plus P2V2. Now, I recognize that the definition for specific enthalpy is U plus PV. So this heat addition is H3 minus H2. Now, hopefully this isn't too surprising. The derivation didn't change between the beginning of lecture and now, but sometimes it's nice to review these things. So I know that as I'm adding heat, if I use a constant specific heat analysis, now because this is delta H, I have to say the mass times Cp times delta T. Usually for closed systems, we're trying to find the change in specific internal energy, and we would use Cv times delta T. But in this case, we want the change in specific enthalpy, so it's Cp times delta T. I know M, I don't know T2, I know Cp, and I know T3. So if I knew T2, I could find the heat that's added to my system. Can I get a symbolic solution for the thermal efficiency? So thermal efficiency, I know, is either net work or net heat divided by Q in. To make my life a little bit easier, and because I've already found Q in, I've used this version of the thermal efficiency equation where I take Q in plus Q out divided by Q in. I can simplify this because Q in is in the numerator and the denominator. So this is 1 plus Q out divided by Q in. Now I recognize that Q out is negative, so my thermal efficiency is still going to be below 100% here. So what do I do next? I know that Q out is going to be from the first law of the simple system between state 1 or state 4 and state 1. So I'm going to cancel out the work term, and I'll get that Q out is U at the end minus U at the beginning. So U1 minus U4. And then I'm going to divide by the Q in, which I've already found the symbolic solution for. Again, I'm going to notice that here I need to use constant specific heats. So my delta U's become Cv times delta T. And my delta H becomes Cp times delta T. I know CV. I don't know T4. I do know T1. I don't know T2. I know CP. And I know T3. So if I knew T2 and T4, then I could find the thermal efficiency. This next part is a little bit trickier. So I want to be able to find the cutoff ratio. So how do I do that? I know that the cutoff ratio is V3 divided by V2. That's just the definition. I look at the heat transfer process and I take the larger volume, that's V3, divided by the smaller volume, that's V2. From the ideal gas law, I know that P2 V2 over T2 is equal to P3 V3 over T3. So I know that V3 divided by V2 is going to be P2 divided by P3. P2 is equal to P3. So V3 divided by V2 must be T3 divided by T2. So if I knew these temperatures, then I could find my cutoff ratio. I don't know T2, but I do know T3. So I could get my cutoff ratio if I knew T2. Okay, so now I have symbolic solutions for all the parts of this problem, right? And what I want to be able to do is get values for all these temperatures so that I can just find the numerical values for all the parts of the problem. So I start with this process, right? So I know everything at state 1. I have the temperature and I have the pressure. So as I move from state 1 to state 2, this is my compression process. So because this is adiabatic and ideal, it's going to be an isentropic process. So I will look, because I'm using constant specific heat, I'll look for an equation that has K in the exponent and gives me the ratio of temperatures as a function of the ratio of the volumes. I can isolate for T2, which is the temperature that I don't know. And I already know V1 divided by V2 because I'm told the compression ratio here. So my temperature is increasing. That's a good thing, right? I'm increasing the temperature as I compress the fluid. That's actually why we get ignition of the fuel in this case. So here, T2 is 1,615 degrees. I'd like to find the pressure in this case, and to do that, I can use the ideal gas law. So as I go from state 1 to state 2, I know P1 V1 over T1 is equal to P2 V2 over T2. I can isolate for P2, which is what I've done here, and P2 is equal to P1 times V1 divided by V2 times T2 divided by T1. I know V1 divided by V2, that's my compression ratio, and I've used my isentropic relationship to find T2 over T1. So I have all the information I need, and I see that the pressure at state 2 is 739.2 pounds per square inch. So this is pretty good. I know state 1 and I know state 2. How do I go from state 2 to state 3? So this is not an isentropic process because here I have to add heat to the system. So I can't use an isentropic relationship, but my working fluid is still an ideal gas, so I can use the ideal gas law. I also remember that as I move between state 2 and state 3, the whole thing that differentiates the Otto cycle from the diesel cycle is that at the diesel cycle, when I'm adding heat, moving from state 2 to state 3, I'm doing so at a constant pressure. So this pressure between state 2 and state 3 is the same for the whole process. So that means the pressure at state 3 is equal to the same pressure at state 2. If I would like to get a ratio between V3 and V2, I can see if I use the ideal gas law that V3 over V2 is equal to P2 over P3 times T3 over T2. But P2 and P3 are the same. So again, I see for my cutoff ratio, V3 divided by V2 is equal to T3 divided by T2. In this case, I now know those values, so I see that my compression ratio is 2.48. So I've already found the answer to part C, just by moving through my states here. So I know that RC is 2.48. Now I want to move between state 3 and state 4. I recognize that this is the second part of my power stroke, the part of my power stroke that's isentropic. So delta S here is equal to 0. And that means that I can use this expression with K in the exponent. Again, I'm looking for an expression where the temperatures, or the ratio of temperatures, and the ratio of volumes exist inside my equation. So now I see that T4 is equal to T3 times V3 over V2 to the power of K minus 1. And this would be great. I would be finished if I knew what V3 divided by V4 was. And this is in a lot of ways, the trickiest part of these diesel cycle problems. We're going to have to do a little bit of sleight of hand here, right? So the first part of my trick is that I remember that V4 is the same as V1. Remember, the heat rejection process happens at constant volume. So V4 is equal to V1. So V3 divided by V4 is the same thing as V3 divided by V1. Now, maybe you're sitting there thinking, how does that even help me? Because there's two ratios I know, right? One is my compression ratio, the other is my cutoff ratio, and neither of those things are V3 divided by V1. So this part is the sleight of hand, right? So I'm going to multiply this expression by 1, right? But I'm going to multiply this by a very special version of 1, and that special version of 1 will be V2 divided by V2. So when I do that, right, so all I've done here is I took V3 divided by V1 and I multiplied by V2 over V2. So multiplying by 1, you're always allowed to do that and you get the same answer. But I've split up my numerator and my denominator so that here I have V2 over V1 and here I have V3 divided by V2. Now the cool thing here is that V3 divided by V2, that's the cutoff ratio. V2 divided by V1 is 1 divided by the compression ratio. So this expression here, V3 divided by V4, is really the cutoff ratio divided by the compression ratio. So I can put that into my equation. And now I know T3, I've worked out the cutoff ratio, and I was given the compression ratio. I know for air, K is about 1.4. So when I put all this information into my equation, I get that T4 is equal to 1,852.1 degrees Rankine. And I can put that into my state table. So now I'm at the happy point where I have symbolic solutions and I have all the variables that I need. I just have to put all this stuff into my calculator without making a mistake. Now, that's not always easy for me to do. Sometimes I fat finger my answers here, but hopefully I can get through the rest of the problem without making a mistake. And if I was on a test, even if I did make a mistake from here on out, I've already demonstrated that I understand how to do these diesel cycle problems. So here we're given the mass flow rate. I know CP, and I know T3, and I know T2. So I find that the heat addition from state 2 to state 3 using a cold air standard analysis, or assuming that specific heat is constant, is just about 83 British thermal units. The answer to part B, what's the cutoff ratio? That's V3 over V2. But I found from the ideal gas law, and remembering that the pressure is constant as I move from state 2 to state 3, that this is the same as T3 divided by T2. And I got that the cutoff ratio was just about 2.5. My thermal efficiency, I haven't calculated yet, but I know CP, I know CV, and I know all of these temperatures. So when I put all this information into my calculator, I get a thermal efficiency of 60%, or 0.6. And that's it for diesel cycles. So hopefully, through these 3 lectures, you've got a good idea of how to tackle these internal combustion engine problems. Essentially, what we need to remember is that internal combustion engines are heat engines. So we characterize them all as being the net power, or the net work, divided by the heat transfer rate in, or the heat in. The next thing we need to know is the system open or closed? So we model all of these processes as closed system processes, even though we know that that's not strictly true. Then we ask, is the working fluid air, or water, or something that looks like it? In this case, our working fluid is an ideal gas, air. And then, in this case, we assumed that we were saying constant specific heat. But for the Otto cycle, I showed you also how to do problems with variable specific heat. So, hopefully, if you can answer those 3 questions, you can start to think about these internal combustion engines in the same way that we thought about Rankine cycle problems, answering these 3 problems, going through this same process. It's a bit of a choose your own adventure, so you're flipping to different parts of the book to figure out how to solve the actual problem. This is the end of our journey into internal combustion engines. Next, we'll look at another cycle where the working fluid is air, another cycle that's a heat engine, but this time it will be called a Brayton cycle, and the Brayton cycle is the type of thermodynamic cycle that we use for natural gas power plants. Remember, we talked about how there's been a surge of usage of natural gas power plants here in the United States. So this is a pretty contemporary issue for us to start looking at. I'll see you next time on Thermodynamics.